Hello and welcome to yet another lecture on power generation and economics, paper code EE704C. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Chandra, Institute of Technology and Sports Complex, Department of Electrical Engineering. Today my topic is an overview on unit commitment. Lesson objective. After end of this lesson, student will be able to understand the basic concept of unit commitment. So, an overview on unit commitment. So, the introduction. Human activities follow cycles. Most systems supplying services to a large population will experience cycles. This includes transportation systems, communication systems, as well as electric power systems. So, it is obvious that the human activity follows the different cycles, such as like the transportation system cycles, the cycles dealing with communication systems, and also the electric power systems. So, in case of an electric power system, so it is obvious that the total load of the system will generally be higher during the daytime and the early morning when the industrial loads are high. The total load of the systems uh, during the daytime and the early evening when the industrial loads are high, and also the lower during the late evening and the early morning when most of the people is asleep. So it is clear that during the daytime and the early evening, when all the industries are on and all the industrial loads are there, the total load of the system is generally high. But in case of the late evening and the early morning, when the most of the population goes to sleep, the load is low. So the daytime and the early evening, the load is high, and the late evening and the early morning, the load is low. And another aspect is that the use of the electric power, that the power we have used, it has a weekly cycle. The load is being lower over the weekend days than the weekdays. So the load that is the lower over the weekend days than the weekdays. So it is clear that the electric power that is supplied to the consumer or the power that is required in our daily life, it has a cycle. And the power demand during the daytime and the early evening when all the industries are on is more compared to the power demand which is less in the late evening and the early morning. So in case of the total week two, the load being lower over weekend days than the weekdays. So obviously a question will arise that why this is a problem in the operation of an electric power system. This is a problem for the operation of an electrical power system. So in order to and another question that will arrive from that particular question is that in our mind that why not simply commit enough units to cover the maximum system load and leave them running? So these two type of question will be arrive that why is this a problem in the operation of an electrical power system? And why not just simply commit enough units to cover the maximum system loads and leave them running? So to commit a generating unit is to turn it on. So the term that is said the commit means we have to turn it on or turn a generator unit on. That is, what does that mean that turn it on a generator unit? It is mean that to bring the unit up to speed, synchronize it to the system and connect it so it can deliver power to the network. So the term commit generating unit means turn it on, turn that unit but on. Why? The required is to bring the unit up to the speed, synchronize the system, synchronize it to the system and connect it so that it can deliver the power to the network that according to the load demand of the consumer. The problem that is commit enough units and leave them online is the economic problem. The main problem regarding to commit enough units and leave them online is economic problem. So a great deal of money can be saved by turning units off when they are not needed. So commit or unit commitment. The term called commit means turn a unit on. And so the why a unit is turned on? The answer is that to bring the unit up to the speed, synchronize it to the system and connect it so that it can deliver power to the network depending upon the load demand of the consumers. But the main problem in case of the commit enough units and leave them online is the economical problem because we want to save a great amount of money by turning the units off when they are not needed. So let us take an example. It is given that there are three units are connected. It named as unit 1, unit 2 and unit 3. So minimum and the maximum generation of that unit is given that the minimum generation for the unit 1 is 150 megawatt and the maximum generation of unit 1 is 600 megawatt and minimum generation of unit 2 is 100 megawatt and maximum generation for unit 2 is 400 megawatt. Minimum generation for unit 3 is 50 megawatt and the maximum generation for unit 3 is 200 megawatt. This is the minimum and the maximum generation of each unit is given. And the H, the term H which stands for fuel input to the unit. The H that is stands for fuel input to the unit and the unit of H is MBTU per hour which is known as millions of BTU per hour and the P that is stands for the unit output in megawatts. So that this P. So the H which stands for fuel input to the unit and in MBTU per hour that is millions of BTU per hour and the P which stands for the P that stands for unit output in megawatts. So H1 and the 1 that is given that H1 for unit 1, H2 for unit 2, H3. 1, 2, 3 stands for unit 1, unit 2, and unit 3. So this is the equation of each one. That is the fuel input to the unit 1, that is the fuel input to the unit 2, and that is the fuel input to the unit 3 in MBTU per hour. And the fuel cost, it is given for the unit 1, the cost is 1.1 rupees per MBTU. For the unit 2, the cost is 1.0 rupees per MBTU. And for the unit 3, the cost is 1.2 rupees per MBTU. So this is a general example of 3 units. So if say we are supplied to a load of 550 megawatt, a load demand of 550 megawatt, what unit or combination of units should be used to supply this load most economically? So let us a load demand of 550 megawatt. So the 3 units, so we have to supply a load demand of 550 megawatt using these 3 units. So obviously a question will arise that which unit or which combination of units we have to run in order to meet those load demand. But keeping in mind that we have to meet those load demand most economically, the economic approach of the load demand. To solve this problem, simply try all the combination of the 3 units. Some combinations will be infeasible if sum of all the maximum megawatts for the 3 units committed is less than the load, or the sum of all minimum megawatts for the units connected is greater than the load. So some will be infeasible where the sum of the maximum megawatt for the units, that is the maximum summation of the maximum megawatt of that units is connected is less than the load, because we have not run those units. If we run those 3 units and their total demand will be more compared to the load demand, so it will be infeasible. It will be infeasible. And also, if the sum of the minimum megawatt for the units committed is greater than the load, it is also infeasible. So we will try all the combination of the units, and we will see that which one is the economical one depending upon the load demand. So let us we are create a table called unit combinations and dispatch for 550 megawatt load. So we are creating a table. Here the unit 1, unit 2, unit 3 are there, and along with the maximum generation, minimum generation, P1, P2 and the P3, that is the unit outputs in megawatts, F1, F2, F3, that the cost that is required, and summation of F1, F2 for the each unit, and summation of the total cost generation will be F1 plus F2 plus F3. Let us take how this table is formed. So when it is seen that both the 3 units are off, that is means maximum generation is 0, minimum generation is 0, so cost is effaced. If the unit 1 is off, unit 2 is off, and unit 3 is on. So unit 3 has a, that we have seen in the example, that unit 3 has a minimum generation of 50 megawatt and maximum generation of 200 megawatt. So it is given that the maximum generation is 200, minimum generation is 50. So what is the total generation? 200 plus 50, 250. And what is our load demand? Our load demand is 550 megawatt. So it is not meet the load demand. So it is also an infeasible. Now, unit 1 is, we are trying all the combination. Unit 1 is off, unit 2 is on, unit 3 is off. So for the unit 2 is on, that is total minimum generation capacity of the unit. Minimum output from the unit 2 is 100 megawatt, that is given, and maximum output for the unit 2 is 400 megawatt. The total output, that is here, the minimum and the maximum generation cannot able to meet the load demand. Here, in this case, the minimum or the maximum generation for a particular, if a single unit, that is the unit 2 is running, so it cannot able to meet the generation of the load demand, that is here the maximum generation is 200, minimum generation is 50, so it is lying between the 50 to 200. So for a single, if this unit 3 is running, it cannot meet the load demand of 550 megawatt. Here it is minimum generation is 100, maximum generation is 400, so it is lying between 100 to 400. So it cannot, the unit 2 when operating singly, so it cannot able to meet the load demand of 550 megawatts. So that it is also infeasible. So let us try with when the three units are connected. How this equation is generated? We will concentrate on a particular thing. Say when the three units are in operation. So it is given that when the three units are operating. So what is the maximum generation? The maximum generation is 600 for unit 1, 400 for unit 2, and 200 for unit 3. So 600 plus 400 plus 200 is 1200 megawatt. And what is the minimum? Minimum for unit 1 is 150 megawatt, unit 2 is 100 megawatt, and unit 3 is 50 megawatt. So 150 plus 100 plus 50, it is 300 megawatt. So it is clear that the maximum generation is 1200 and minimum generation is 300. So it is lie between the range of 300 to 1200. So 550 megawatt load demand can be easily met when the three units is in running condition. Now, which unit? Now another question is there. It is seen that the three units is in running condition. It is meeting our load demand of 550 megawatt. That is given that our load demand is 550 megawatt. So it is our load demand is meeting here when the three units are on. Now another question will arrive that which unit will operate less. So it is totally, let us, when the three units is on for per MBTU, first unit we have to pay 1.1 rupees, for second unit we have to pay 1.0 rupees, and for third unit we have to pay 1.2 rupees. Now it is clear in your mind that between the three fuel costs, the fuel cost of the unit 3 is maximum. It is 1.2 rupees per MBTU. So we are approaching in the in economical way, in an economical way. So if we keep it in mind the economical conception of power generation, it is clear that the fuel cost for the unit 3 is more. So it will give the minimum power. Minimum power means the output from the unit 3 is minimum. So the minimum power is 50 megawatt. Okay, so out of 550 megawatt, the minimum power will be given by the unit 3, which is 50 megawatt, because its fuel cost is more compared to the two units. So it is clear that the P3, the generation of power P3 is 50. So the five less 500 megawatt will be given by these two units, and it will given by the approach of economic load generation approach of the units in order to divide the power between the two unit 1 and unit 2, and how we will see it. So it is clear that our total demand, the P load, our total demand is clearly seen that 550 megawatt. This is our total load demand in our problem. So it is obviously also seen that having a higher cost for the unit 3, so it will generate the minimum power. So unit 3 is generating the minimum power of unit 3 is generating the minimum power of 50 megawatt. That is given in the example. It is generating minimum power because its cost is maximum. So 550 minus 50, the rest of the load demand will be given by the remaining two units, that is P1 and P2. They have to give the 550 minus 50, that is 500 megawatt. This is our equation number one. So there are two variables, that is P1 and P2. So we need two equations, uh, that is in order to solve the problem. So let us take the fuel cost, that is F1, which is a function of P1. P1. So the fuel cost is that the in the example, the H1 that is given for an MBTU per hour, that is the fuel input to the unit 1, is H1, P1, and rupees per fuel cost per MBTU, that is given 1.1 for the unit 1. So total cost became, we multiply it with 1.1, so the total cost of the cost equation became this one, 561 plus 1.1 is coming from their fuel cost, 7.921, 7.921 plus, this is a simple multiplication, 0.00156 to P1, P1 square. So same in case of the unit 2, that is if this is for unit 1 and this is for unit 2, that is F2 P2. And it will give, this is for unit 1 and it is for unit 2. This is for unit 2. And F2 P2 became same in this way, that H2 P2 into the fuel cost is 1.0. H2 P2 is given in the example 1. All these H1 P1 are given in the example 1. So this is became same as previous, 310 plus 7.85 P2 0.00194 square. Now, if I use the conception of, we have to keep in mind the economic load generation conception. So, if I use the conception of economic load generation, it will become first order derivative of cost function, that is dd, with respect to the power output dd var, it will be equal to d of e2 f2. So this is called the economic or generation approach. So it will be remain same. So after doing that derivative with this one with respect to h1, if we have p1, and we have done the derivative with respect to this equation with respect to p1, and this equation with respect to p2. So we are getting another equation that is called this one 0.003124 just p1 minus 0.00388 p2 equal to minus 0.07. So this is our equation number 2. So we are getting two equations. One is equation number 1 and equation number 2. And using the two equation, we can easily find the value of P1. It is from that two equation we can easily find the value of P1. It is called the P1 is 267 and P2 is 233. So that is why how we can able to calculate the P1 and P2 for in order in keeping in mind the economic load generation conception. How economically we can able to calculate the value of P1 and P2, keeping in mind the economic load dispatch conception. So now we are concentrate on the cost F1, F2, and F3 required for each of the unit. So let us concentrate on the total cost required. So for say F1, the cost will be become just putting those values on the equation that we have obtained, the equation of F1 after multiplying it, after multiplying H1 with 1.1, we are getting this equation. So just putting those values in this equation, that is 561 plus 7.92 that we are getting into 267 for P1, that the power output that we are getting plus 0.00388 zero zero 1562 into 267 whole square. So the total cost that we have received is that 2787 for unit 1. Now for unit 2, that is the F2, that we have calculated that it is 310 plus 7.85 into 233, that the power, just putting the values of P1 and P2 in the equation. The P1, P2 that we have calculated, we just putting those values of P1 and P2. First equation, 0, 0, 1, 9 into 2, 3 square. So the equation output is 2, 2, 2, 4, 2, 2, 4, 4, 2, 2, 4, 4 rupees. And for the unit 3, that is for unit 1, the cost, that is for unit 2, the cost, that is for the unit 3, cost. So for unit 3, the H3 we can, unit 3 is supplying 50 megawatt of the load, 78.0, just putting the value of P3, that is 50. Here we are putting the value of P1, that is P1 value, that is P2 value, and we are putting the value of P3, that is 50. So it will become the equation 7.97 into 50 plus 0.00482, 0.00482 into 50 square. So this 50 or this 50 square, all are the P3 that is unknown. So it will become 4, 8, 8.55. So what is the cost? The cost F3 can be written as cost of F3 can be written as 488.55. We have known that it is rupees per NBTU is 1.2, 1.2 for the unit 3. So it will be 586. So this is the cost for unit 3. So what is the total cost? total cost is the summation of these three costs. For unit 1, this one, for unit 2, this one, for unit 3, this one. So 2787 plus 2244 plus 586. So the total will be 5617, the total rupees. So in this way, the cost for the each unit and the total cost is determined. So it is clear that whatever we have seen that total maximum generation is, that we have already known that 1200 minimum is 300, and from there, depending upon the fuel cost, the 500, 550 load demand, the 50 is given by the P3, and with the conception of economic power generation, uh, P1 is delivered in 267 and P2 is delivered in 233, and the cost for the P1 is 2244. For cost for the unit 1 is 2787, unit 2 is 2244, unit 3 is 586, and the total cost is 5617 when the three units is on, and all the calculation that we have seen. Cost for the unit 1 is 2787, unit 2 is 2244, and unit 3 is 586. So total cost is 5617. And also, it is seen that in this way, the entire table is designed keeping in mind that we are trying all the combinations, and the corresponding cost is also determined for each unit and the total cost. In this way, keeping in mind all the combination that we have tried, this entire table is created. Now, suppose the load follows a simple peak valley. This is the peak valley load pattern as shown in the figure B. So, our maximum, say the demand is 1200, and it is fallen to the 500 megawatt. Now, when and that is the time duration that is given. So our main concentration is that from this two graph, one is called the unit commitment schedule using shutdown rule. So we are now concentrate that which unit we have to shut down. So beside the shutdown rule, it is clear that the which unit is also running. When I shut down, say the three units is running. When I shut down, if I know the shutdown rule, means we are shutting down our unit, say unit 3. So means besides, it will also give an idea that unit 1 and 2 are in running condition. So if the operation of the system is to be optimized, units must be shut down as the load goes down and then recommitted as it goes back up. We should like to know which units to drop and when. Now, we have seen that when the three units are in running condition, the maximum generation is 1200, and the minimum generation is 300. So it's a peak value load pattern. A load pattern that is obtained is called the peak value load pattern. Say the load demand is 1200. So it is obvious that when the load demand is 1200, we have to run all the three units, units 1 and unit 2 and then unit 3. So now, when the load demand say in this area, uh, when the load demand is here in this area, so say it is the area of say one load demand is So when unit 1 and 2 is running, the maximum demand is 100, means the 1000. It is the 600 plus 400. There is the maximum demand of unit 1 and 2. So it is 1000. So means in between 1000 to 1200. In between 1000, say this is the 1000. So in between 1000 to 1200, all the three units are. If the load demands is like between the 1000, above the 1000 and 1000, we have to run the three units. But if the load demand falls below the 1000, so unit 2 and unit 1 and unit 2 is sufficient enough to meet that load demand. Yeah. So now, same here in this case when the load is increasing, and same here in this case. And the main thing is there in that particular portion when the load is fall down below the 600 megawatt. When the load is falling below the 600 megawatt, which unit we have to run? Say the load demand is, here it is seen in the 500 megawatt. I am telling a load demand of say 100 megawatt. So you will run the unit 3. The answer is no, because the unit 3 has a generation in between 50 megawatt minimum generation and maximum generation is 200 megawatt that we have already seen. For the unit 3 it is 50 and 200 megawatt. So if the load demand is 300 megawatt, we cannot, if the load demand is say 150 megawatt, unit 3 is sufficient. But we cannot run the unit 3 because it has a fuel cost rate is more, 1.2 rupees. And also that, uh, so in this, we have to, so for that particular purpose, we have to run the unit 1 here, because we can also run the unit 2 here, because for the because unit 2 have a most economical approach is to run the unit 2, because unit 2 have a minimum demand of 100 megawatt and maximum demand of 400 megawatt, and say our load demand is 150. So we most economic approach is to run the unit 2, because unit 2 have a fuel cost of 1.0. But here, but say when the load demand is 550 megawatt or say 500 megawatt, when the load demand is 550 and 500 megawatt, we cannot run unit 2 or 3, because unit 2 has a range of 100 to 400 megawatt, unit 3 has a range of 50 to 200 megawatt. So we have to run the unit 1, and it is clearly seen in this figure. We have to run the unit 1 because the load demand is 500, and keeping in mind the economical load, the economic way to run the unit, we have to run the unit 1. So this is the peak value pattern, and this is also the unit commitment schedule using shutdown rule, and keeping in mind that we are which unit we have to shut down means which size shutdown we have to, which unit are in the running condition. So it is clear that which unit we have to run depending upon their minimum and maximum demand. And also keep in mind the most important thing is the fuel cost, because say again I am repeating that particular part. Say the load demand is 100 megawatt, so unit 3 is capable enough to run the 100 megawatt because its range is 50 megawatt to 200 megawatt. But we cannot run the unit 3 because unit 3 has a fuel cost of 1.2 rupees per mbtu. So in this way, for the 500 megawatt or the range from the 400 to the 600 range, means this range, the 500 megawatts, in between this range the 500 megawatts is also lying. So we have to run the unit 1 because unit 2 has the limitation of 100 to 400 megawatt. So in this way the schedule has been done and with the peak value pattern. So one approach to this solution is demonstrated in the example 1.1b, that is, a simple priority list scheme is developed. Say example 1b is that suppose we wish to know which unit to drop as a function of load. Let us the units and the fuel cost be same as in the example 1a that we have seen, with the load varying from the peak load from 1200 megawatt to a value of 500 megawatt. To obtain a shutdown load, simply use a brute force technique, wherein all combination of the units will be tried as we have already done in the example A. For each load value taken up taken on steps of 50 megawatt from 1200 to 500. The result of the applying these brute force techniques are given in the table 1.2 in the next table. So there is a maximum, the load is varying from 1200 to 500 megawatt in steps of 50 megawatt, and which combinations of the unit that will shut down we will see in the this table. So a simple shutdown technique is that I have already told that when the load is above 100 megawatt, run all three units. Between 100 and 60 megawatt, run units 1 and 2. Below 600 megawatt, run on unit 1. The reason that I have already told that when the load is above 100 megawatt, run all the three units. Between 100 megawatt and 600 megawatt, run units 1 and 2. Between below 600 megawatt, run only unit 1. So this technique we will apply in the table to the shutdown loop. So, load demand is 1200 megawatt. We have to run all the three units till, and it's a step of 50 megawatt. So the next is 1500. So we have to run all the units. 1100. We have to run all the units up to which portion? Up to the portion of 1000. When the unit 3 is off, because the maximum demand for unit 1 and 2 is, if I sum the maximum demand for unit 1 is 600 and unit 2 is 400, so 600 plus 400 is 1000 megawatt. So 1000, 950, 850, and up to that particular 650, all unit 1 and 2 are on, means unit 3 is off. Now when the load demand is 600, so when the load demand is 600, the maximum demand for the unit 1 is 600 and maximum demand for the unit 2 is 400. So we have to run the unit 1 and we have to off the unit 2, and unit 3 is already off for the load below uh, load demand below the 600. So it is clear that when the 600, unit 1 is on, unit 2 and 3 is off. 550, units 1 is on, units 2 and 3 is off. For 500 up to 500, from 1200 to 500, a step of 50 megawatt, unit 1 is 1 and units 2 and 3 is off. So in this way the shutdown rule can be applied. So so far that we have obeyed one simple constraint: enough units will be committed to supply the load. If there were all that was involved in the unit commitment problem, that is just meeting the load, we could stop here and state that the problem was solved. Unfortunately, other constraint and other phenomena must be taken into the account in order to claim the optimal solution. So we have only concentrated on the we have to concentrate on the another constraint, because we have only concentrate on the just not meeting the load. We have only concentrate on the simple constraint, or one simple constraint that we have obeyed. So we have to consider the other constraint in order to find the optimal solution. So today we have learned about a basic conception of unit commitment. Thank you.